This topic introduces the scope and role of fluid mechanics as a foundation in engineering. The focus is on understanding basic concepts before moving into more mathematical analysis. The discussion covers how fluids are defined, how they behave, and why they are important in engineering systems. The approach is both conceptual and application-oriented. This chapter becomes the basis for all subsequent topics in fluid mechanics. The course structure shows that the discussion starts from basic concepts and progresses to internal flow applications. The chapter sequence is designed so that understanding develops gradually from fluid properties to momentum analysis. Each chapter is interconnected and forms a complete analytical framework. Mastery of the early chapters strongly affects understanding of later topics. This outline helps locate the current topic within the whole course. The learning objectives emphasize conceptual understanding rather than formula memorization. Students are expected to identify various types of real-world fluid mechanics problems. Modeling and problem-solving processes become the core competencies to be developed. Attention to units, accuracy, and precision is also strongly emphasized. The final goal is the ability to think systematically in solving engineering problems. Fluid mechanics studies the behavior of liquids and gases, both at rest and in motion. The analysis includes the forces acting on fluids and their effects on fluid behavior. This field is essential in designing systems such as river flows, aerodynamics, and hydraulic systems. Its role extends to many engineering disciplines and environmental sciences. Without fluid mechanics, many modern engineering systems could not be properly designed. Shear deformation is illustrated using a rubber block subjected to forces parallel to its surface. This force causes layers of the material to slide relative to each other. Shear stress develops inside the material as a response to this force. This concept is important for understanding how fluids and soft materials behave under load. It becomes the foundation for the concept of viscosity in fluids. Normal stress acts perpendicular to a surface, and in static fluids, it is represented by pressure. Shear stress acts tangentially to the surface and only appears when the fluid is in motion. In a static fluid, no shear stress exists. This shows that pressure is the only relevant stress in fluids at rest. This distinction is fundamental in separating fluid statics from fluid dynamics. This section reinforces the idea that in static fluids, no shear stress exists. Pressure becomes the only form of stress present. This concept must be fully understood before moving to fluid flow analysis. Misunderstanding this point will affect many later analyses. This question tests conceptual understanding rather than calculation skills. Liquids form a free surface when they do not completely fill a container. Gases always expand to fill the entire volume of their container. The density of liquids is nearly constant, while gas density strongly depends on pressure and temperature. These differences are crucial in engineering modeling and analysis. Treating a gas like a liquid can lead to serious errors. Phases of matter. In the solid phase, molecules are tightly packed and remain in fixed positions. In the liquid phase, molecules stay close but can move and flow. In the gas phase, molecules move freely and fill the entire available space. These molecular arrangements explain the different mechanical properties of each phase. Fluid mechanics mainly focuses on the behavior of liquids and gases. Understanding pressure. Microscopically, pressure comes from molecular collisions with the container walls. Macroscopically, pressure is measured using instruments such as pressure gauges. The measured value represents the cumulative effect of these molecular interactions. Pressure is a key variable in many engineering systems, such as engines and pipelines. Understanding pressure is essential before studying fluid statics and dynamics. Fluid dynamics in artificial hearts. The application of fluid mechanics in artificial hearts focuses on controlling blood flow in a stable and safe manner. Improper flow can cause clotting or tissue damage. The system design must mimic the flow behavior of the natural human heart. Pressure and flow velocity become critical parameters. This example shows that fluid mechanics is important not only in industry, but also in medicine. Check your understanding number 2. This question emphasizes that the main purpose of fluid mechanics in artificial hearts is to ensure efficient and safe blood flow. The focus is not on electrical efficiency or device weight. Poor flow behavior can create serious risks for patients. Therefore, fluid aspects become central in the device design. This question tests understanding of application rather than simple definitions. Applications of fluid mechanics. Fluid mechanics is used to model natural systems, such as weather, ocean currents, and river flows. In engineering, it is essential for power plants, aircraft, and vehicles. In medical and industrial fields, fluid mechanics supports the design of artificial organs and piping systems. Almost every system involving flow requires fluid mechanics analysis. This shows the wide scope and impact of this field. Pergamon pipeline. The ancient clay pipelines in Pergamon show that fluid mechanics principles were used long ago. The system was able to transport water over long distances efficiently. The relatively small pipe diameters indicate an understanding of pressure and flow. This infrastructure proves that fluid engineering is not purely a modern science. This example shows how water needs have driven technological development for centuries. Reversible water wheel. Water wheels were used as a source of mechanical energy from flowing water. This system enabled the lifting of heavy loads in mining. Renewable energy was already being used long before modern concepts existed. The basic principle of converting fluid kinetic energy into mechanical work was already applied. This example shows the close relationship between fluid mechanics and energy conversion. Reynolds apparatus. This apparatus is used to demonstrate the transition from laminar to turbulent flow in a pipe. The change in flow pattern is influenced by velocity, viscosity, and pipe diameter. From this experiment, the Reynolds number was introduced as a key parameter. Dye is used to visualize the flow patterns directly. This concept became fundamental in pipe design and aerodynamics. Check your understanding. Number 3. This question emphasizes that the Reynolds number is used to predict the type of flow. This concept comes directly from experimental observation, not purely from theory. Understanding the Reynolds number is essential in almost all flow analyses. Without this parameter, flow classification becomes unclear. This question ensures the link between experiment and theory is well understood. The Wright brothers' flight. The first successful powered flight demonstrated the real application of aerodynamic principles. The concepts of lift, thrust, and control were the keys to this success. This achievement marked the beginning of the modern aviation era. Fluid mechanics played a major role in the development of aircraft afterward. This example shows how fluid theory directly impacts technology. Wind turbine evolution. Modern wind turbines show major improvements in efficiency and power capacity. The kinetic energy of wind is converted into electrical energy through fluid mechanics principles. Changes in design and scale significantly improve system performance. This example highlights the role of fluid mechanics in renewable energy. flow engineering becomes the key to maximizing energy output. No-slip condition. The no-slip condition states that the fluid velocity at a solid surface is equal to the velocity of that surface. If the surface is stationary, the fluid velocity at the contact point becomes 0. Farther away from the surface, the fluid velocity increases until it reaches the free stream value. This phenomenon occurs due to viscosity and adhesion between the fluid and the surface. This concept is crucial in analyzing friction and drag forces. Check your understanding number 4. This question reinforces that the velocity profile shows the variation of velocity from 0 at the surface to the free stream velocity. This is a direct consequence of the no-slip condition. This understanding is essential in boundary layer analysis. Without this concept, the distribution of shear stress cannot be explained. This question tests physical understanding rather than memorized definitions. Flow over a surface. A fluid in contact with a stationary surface has 0 velocity due to the no-slip effect. Fluid layers farther from the surface move faster, creating a velocity gradient. This velocity profile shows how momentum is transferred from the main flow toward the wall. This phenomenon forms the basis of boundary layer development. Many engineering applications, such as turbines and heat exchangers, depend on this understanding. Flow separation. Flow separation occurs when the fluid detaches from the surface it is flowing over. The main cause is an adverse pressure gradient that slows down the near-wall layers. When the momentum is not sufficient to overcome the pressure rise, the flow separates. This phenomenon increases drag and energy losses. In aerodynamics and pipe design, flow separation should be avoided as much as possible. Viscous and inviscid flow. Near the surface, viscous effects dominate and cause the formation of a boundary layer. Far from the surface, viscosity effects are often small, and the flow can be treated as inviscid. This separation of regions helps simplify complex flow analysis. This approach is widely used in aerodynamics and hydrodynamics. Even with simplification, viscous effects near the wall must still be considered. Check your understanding. Number 5. This question emphasizes that friction near the surface leads to the formation of a boundary layer. This layer is the region where viscous effects become significant. Without the boundary layer concept, many flow phenomena cannot be explained. This question links the physical idea to the correct technical term. It ensures that the term boundary layer is understood conceptually. Flow around a sphere. Flow around a sphere is a very common example of external flow. A turbulent wake forms behind the sphere and increases drag. This flow pattern is strongly influenced by the Reynolds number. This phenomenon is important in sports, such as tennis, and also in engineering. Shape optimization aims to reduce the wake and the drag. Shock wave dynamics. The bursting of a balloon produces a nearly spherical shock wave that can be visualized using Schlieren methods. In addition to the main shock, secondary shocks appear and create complex patterns. This phenomenon illustrates the behavior of high-speed gas flows. The study of shock waves is very important in supersonic aerodynamics. This example shows that fluid mechanics also includes compressible flows. Flow regimes. Laminar flow is characterized by smooth and orderly motion with very little mixing. Transitional flow represents an intermediate stage with increasing disturbances. Turbulent flow is chaotic and involves strong mixing. The change between these regimes is strongly influenced by the Reynolds number. This classification is important for choosing the correct analysis model. Check your understanding. 6. This question reinforces that the main characteristic of turbulent flow is its chaotic nature and strong mixing. This type of flow is very different from the orderly laminar flow. Understanding this difference is important for analyzing friction and energy losses. This question tests the ability to distinguish the physical characteristics of each flow regime. The focus remains on concepts rather than calculations. Thermal plumes around bodies. Warm air around a body rises because its density is lower than the surrounding air. This motion forms a thermal plume that can be visualized. This phenomenon is an example of natural convection. This process plays an important role in heat dissipation in humans and animals. The concept is also relevant in the design of ventilation and passive cooling systems. Visualizing flow. A short exposure photograph captures the chaotic flow at a single instant in time. A long exposure photograph averages out fluctuations and produces a smooth-looking flow pattern. Both methods provide different information about flow behavior. Flow visualization is very helpful for understanding phenomena that are difficult to describe mathematically. This technique is widely used in research and education. Airfoil wake analysis. The instantaneous wake shows unsteady and oscillating flow patterns behind the airfoil. The time-averaged wake shows a smoother pattern representing the mean flow behavior. This difference is important in analyzing drag and flow stability. This visualization helps explain the sources of vibration and noise. This concept is very important in aerodynamic design. Pipe flow development. In the pipe entrance region, the flow is still two-dimensional and the velocity profile is developing. Farther downstream, the velocity profile becomes stable and no longer changes in the flow direction. At this point, the flow is fully developed and can be treated as one-dimensional. The entrance length depends on the Reynolds number. This concept is important in calculating pressure losses in pipes. Check your understanding number 7. This question emphasizes that fully developed flow can be treated as one-dimensional. In the entrance region, velocity still varies in two directions. After a sufficient distance, the velocity profile no longer changes along the pipe. This understanding is important for simplifying pipe flow analysis. This question ensures that the term one-dimensional is properly understood. Flow around a car antenna. Most of the flow around the antenna can be considered two-dimensional. However, near the top and bottom regions, three-dimensional effects become significant. This simplification helps in aerodynamic analysis of vehicles. This approach is often used to reduce computational complexity. This example shows how assumptions are intelligently applied in engineering. Axisymmetric flow. Because of its shape, the flow around a bullet is symmetric about its central axis. This flow pattern simplifies analysis because only one plane needs to be considered. Streamlined design aims to maintain this stable flow pattern. This reduces drag and improves motion efficiency. This concept is important in the design of projectiles and high-speed vehicles. System and surroundings. A system is the part of the universe chosen for analysis. The system boundary separates the system from its surroundings and can be real or imaginary. Energy or mass can cross this boundary. Properly defining the system is essential before writing the governing equations. A wrong system definition will lead to incorrect analysis. Closed system with moving boundary. A closed system has a fixed amount of mass, but energy can cross its boundary. If the boundary is allowed to move, the system volume can change during the process. A classic example is a piston cylinder system. This model is widely used in thermodynamics and fluid mechanics. This understanding is important for writing correct energy balances. Check your understanding number 8. This question emphasizes that the main characteristic of a fixed mass system is that its mass does not change, while energy can be transferred. This distinguishes it from a control volume. Many students often confuse these two concepts. This question helps reinforce the difference. The focus remains on understanding the basic system concept. Control volume boundaries. A control volume can have real or imaginary boundaries for the purpose of analysis. These boundaries may be stationary or moving, depending on the system being studied. Mass and energy can cross these boundaries. This approach is widely used in analyzing turbines, nozzles, and flow systems. Choosing the correct control volume boundary greatly affects the simplicity of the analysis. SI units and prefixes. The SI system defines base units, such as meter, kilogram, and second. To handle very large or very small scales, prefixes such as kilo and micro are used. This system allows consistent scientific communication worldwide. Without unit standardization, engineering calculations would be difficult to compare. Therefore, SI becomes a common language in engineering and science. SI prefix applications. SI prefixes such as milli and mega make it easier to express very small or very large numbers. This avoids using too many confusing zeros. This system is widely used in many engineering and scientific fields. The examples show how flexible this system is in practice. Mastery of SI prefixes is essential for reading and writing engineering data correctly. Force unit definitions. The Newton is defined as the force required to accelerate a 1 kilogram mass at 1 meter per second squared. In the English system, the pound force is defined based on the acceleration of one slug. Both definitions show the relationship between force, mass, and acceleration. Understanding these definitions is important to avoid confusing mass and force. Many calculation errors come from misunderstanding this concept. Force units comparison. This comparison gives an intuitive sense of the magnitude of different force units. The Newton, kilogram force, and pound force are compared using apples as an analogy. This approach helps build physical intuition about force. Although simple, this analogy is very effective for beginners. This intuition is important before moving into more abstract calculations. Check your understanding. Number 9. This question tests understanding of the magnitude of 1 pound force in an intuitive way. By imagining apples, the concept of force becomes easier to understand. This approach helps avoid confusing mass and force. The question reinforces the link between units and their physical meaning. The focus remains on understanding rather than memorizing numbers. Weight variation on moon. The weight of an object depends on the local gravitational acceleration. On the moon, gravity is much smaller, so the weight becomes about 1/6 of that on Earth. However, the mass of the object remains the same everywhere. This example clearly distinguishes mass from weight. This understanding is very important in mechanics and fluid mechanics analysis. Unit mass weight at sea level. 1 kilogram of mass has a weight of about 9.807 newtons at sea level. In the English system, 1 lbm has a weight of 1 lbf under standard gravity. This example shows the direct relationship between mass and weight through gravity. This concept is often misunderstood in practice. Therefore, mass and weight must always be clearly distinguished. Energy from a match. Burning a single match releases about 1 kilojoule, or 1 BTU of energy. This example gives a sense of the energy scale in everyday life. Although small, this energy still follows the law of energy conservation. This analogy helps in understanding the magnitude of energy units. This intuition is important before analyzing much larger energy systems. Importance of unit consistency. All terms in an equation must use consistent units to obtain correct results. Inconsistent units almost always lead to errors. Many major engineering failures started from unit mistakes. Checking units is a simple but very important step. This habit should always be applied in every engineering calculation. Unity conversion ratios. Conversion factors are used to change units without changing the physical value of a quantity. The basic principle is multiplying by a ratio that equals 1. In this way, the unit form can be safely changed. This method is very important when switching between SI and imperial systems. Without this technique, unit errors would occur frequently. Check your understanding, number 10. This question emphasizes that the main function of conversion factors is to maintain unit consistency. The physical numerical value should not change because of conversion. Many student mistakes occur due to misunderstanding the purpose of conversion. This question reinforces the idea that conversion is a tool, not a source of physical change. The focus remains on the meaning of units, not just numbers. Weight-mass relationship. In the English system, a practical assumption is often used, that 1 pound mass equals 1 pound force on Earth. This assumption is only valid when standard gravity is assumed. Physically, mass and weight are still different quantities. This simplification must be used carefully. Proper understanding is still required for more precise analyses. Metric system quirks. In everyday metric usage, the word kilogram is often used to refer to weight, even though it is scientifically a unit of mass. This habit can cause confusion in engineering contexts. The distinction between mass and weight must always be kept clear. In engineering calculations, using the correct terms is very important. This conceptual accuracy prevents misinterpretation of results. Mathematical modeling process. The first step is to identify important variables and relevant physical laws. Then, assumptions and simplifications are made to make the problem manageable. Differential equations are formulated based on the physical model. The solution is obtained by applying initial and boundary conditions. This process is the core of engineering modeling. Simplified modeling in engineering. Simplified models aim to capture the main characteristics of complex systems. The helicopter example shows how the rotor can be modeled as a disk. The helicopter body can also be simplified into an ellipsoid shape. In this way, pressure and flow analysis becomes much easier. This simplification does not remove the main physics of interest. Check your understanding. Number 11. This question emphasizes that the helicopter rotor is modeled as a disk to simplify the analysis. The goal is to make the study of air pressure distribution easier. This model does not represent the exact real shape, but it is sufficient for initial analysis. Such an approach is very common in engineering. This question tests understanding of the purpose of modeling, not the actual shape. Step-by-step problem solving. A systematic approach makes complex problems easier to solve. Large problems are broken down into smaller, logical steps. This reduces the risk of conceptual mistakes. This process also helps trace the source of errors if the results do not make sense.
This method is an important habit in engineering. Reasonable assumptions. When data are incomplete, assumptions must be made, so the problem can still be analyzed. However, unreasonable assumptions can lead to large errors. Good assumptions only cause small deviations from reality. The ability to choose appropriate assumptions is an important engineering skill. This is the difference between smart and dangerous simplification. Result verification. Calculated results must always be checked for physical reasonableness. Comparing conditions before and after modifications helps evaluate whether performance has truly improved. If the results show behavior that contradicts intuition, there is likely an error. This step is often neglected, even though it is critical. Result verification is an essential part of responsible engineering practice. Check your understanding number 12. This question emphasizes that the purpose of result evaluation is to ensure that modifications truly improve performance. The focus is not on cost, weight, or administrative aspects. Engineering analysis must always be linked to the physical performance of the system. This question helps build the habit of thinking critically about calculated results. The core idea is to ensure that changes bring real improvement. Accuracy versus precision. Accuracy indicates how close a measurement is to the true value. Precision indicates how consistent repeated measurements are. A measurement can be precise but not accurate, or accurate but not precise. The ideal goal in engineering is to achieve both at the same time. The shooter example helps build intuition about this difference. Significant figures. The number of significant figures in a result should not exceed those in the original data. Showing too many digits gives a false impression of accuracy. Rounding must be done consistently with data precision. This rule maintains scientific honesty in reporting results. This habit is very important in engineering and scientific reports. Significant digits. Significant digits are the digits that carry meaning in a numerical value. Leading zeros are not significant, while trailing zeros may or may not be, depending on the notation. Scientific notation helps clarify the number of significant digits. This understanding is important for reading and writing experimental data. Without this concept, measurement results can easily be misinterpreted. Instrument accuracy and resolution. High resolution of an instrument does not always guarantee good accuracy. A simple instrument can sometimes provide more reliable results. Accuracy depends on calibration and instrument quality, not just the number of digits. The stopwatch example clearly illustrates this difference. Instrument selection must consider both aspects. Check your understanding. Number 13. This question emphasizes that high resolution does not guarantee better accuracy. Many people mistakenly think that more digits mean more correctness. This question helps correct that misunderstanding. The focus is on measurement quality, not on number display. This is a very important concept in engineering experiments and measurements. References. This section shows the main sources of figures and materials used in the lecture. The primary reference comes from the book by Chengal and Chimbala on fluid mechanics. Using this source ensures that the material follows international standards. References are also important for students who want to study more deeply. This practice builds a good academic culture.